Welcome to our exploration of one of the most fascinating concepts in modern physics, the dual nature of matter and charge. Today, we'll dive into how every particle, even at rest, can exhibit wave-like properties. This idea, which bridges the worlds of classical and quantum physics, has revolutionized our understanding of the universe. From the earliest philosophical debates to the latest scientific experiments, the journey to this realization is filled with curiosity, discovery, and a touch of wonder. Let's begin by setting the stage for our journey into the world where charge behaves like a wave. Before we delve deeper, it's important to recognize the collaborative nature of scientific progress. Every breakthrough is built on the support and insights of others. In this project, gratitude is extended to family for their unwavering support, to mentors for their guidance, and to the inspiration that drives scientific inquiry. This spirit of appreciation reminds us that science is not just about equations and experiments, but also about the people and relationships that make discovery possible. The mid-20th century, the wave nature of matter was fully accepted, especially after the success of electron diffraction experiments. This led to the realization that particles don't just behave as solid objects, they can also act like waves. The de Broglie hypothesis provided a mathematical framework for this duality, but it also revealed certain limitations. For example, the original formula doesn't apply when a particle's mass or speed is zero. In this video, we'll explore how this relationship can be modified to overcome such problems and why understanding the wave nature of matter is fundamental to physics. Guide our journey, let's take a quick look at the structure of our discussion. We'll start with an introduction to charge and the wave nature of matter, followed by the background and objectives of the study. Next, we'll address the core problems and review key literature, including the behavior of particles as charges and waves, and the reasons behind the emergence of wave properties in all matter. Finally, we'll conclude with a summary and references. This roadmap will help us navigate the complex but fascinating landscape of quantum physics. Study of static electricity dates back to ancient Greek philosophers, who discovered that rubbing amber could attract straw. This simple observation laid the foundation for understanding electric charge. Later, English physicist William Gilbert expanded on these ideas, identifying two types of electrical properties. The concept of electric charge became central to physics, with the unit of charge, the coulomb, named after French physicist Charles-Augustin de Coulomb. These early discoveries set the stage for the modern understanding of charge as a fundamental property of matter. Electric charge comes in two forms, positive and negative. This distinction was first formalized by Benjamin Franklin, who could have named them anything, but chose these terms for their mathematical convenience. The interaction between charges, attraction and repulsion, forms the basis of many physical phenomena. The discovery that atoms contain both positive and negative charges, with electrons being the first negatively charged particles identified, was a major milestone in atomic theory. 1897, English physicist J.J. Thomson discovered the electron while studying cathode rays. By manipulating electric and magnetic fields, he was able to determine the charge-to-mass ratio of this new particle. This discovery not only confirmed the existence of subatomic particles, but also paved the way for the development of quantum theory. Understanding the electron's properties was crucial for later insights into the wave-particle duality of matter. In 1908, Ernest Rutherford had demonstrated that the positive charge of the atom is concentrated in a tiny nucleus which contains most of the atom's mass. Electrons orbit this nucleus, creating a cloud of negative charge around it. Later, James Chadwick discovered the neutron, a neutral particle with a mass similar to the proton. These discoveries completed the basic picture of atomic structure and set the stage for quantum models of the atom. 1913, Niels Bohr introduced the first quantum model of the hydrogen atom, explaining the quantization of angular momentum for electrons. This model helped physicists understand why electrons occupy specific energy levels and why atoms emit light at certain frequencies. Bohr's ideas were instrumental in leading scientists to question the true nature of particles and waves, especially as they relate to light and matter. Students often struggle with the concept of wave-particle duality, especially when it comes to light and electrons. In our everyday world, we're used to thinking of objects as either particles or waves, but quantum physics shows that things like photons and electrons can behave as both. This duality is at the heart of quantum mechanics and challenges our classical intuitions about the nature of reality. 1923, French physicist Louis de Broglie proposed that all matter, not just light, exhibits both wave and particle properties. His hypothesis was confirmed experimentally in 1927, when electron diffraction was observed. De Broglie's mathematical formulation allowed scientists to calculate the wavelength associated with any particle, fundamentally altering our understanding of matter at the smallest scales. The main goal of this study is to understand why all particles and matter exhibit wave-like behavior. Specifically, it aims to address the properties of charge and matter, how residual charge changes with particle speed, and why wave and mass are inseparable. These objectives guide the investigation into the fundamental nature of matter and its dual characteristics. Nature is the best teacher if we take the time to observe. The inspiration for this study came from a real-life event, a near-miss with a fast-moving truck. This incident led to reflections on non-contact forces such as electrostatic forces and how they might arise from the behavior of electric charge. Such everyday experiences can spark profound scientific questions about the forces that govern our world. In the mid-20th century, the wave nature of particles was widely accepted. However, physicists realized that particles could also exhibit another property, charge behavior. To understand this, we can look at the simple atomic model of hydrogen. Here, the total energy of the electron is the sum of its electrostatic potential energy and kinetic energy, which must equal the electron's total energy in wave form. This scenario can be expressed mathematically, providing a bridge between classical and quantum descriptions. When we rearrange the equations describing the energy of an electron, we find that the charge of the electron is not necessarily constant. Instead, it depends on both the angular momentum and the speed of the electron during its motion. This insight reveals a deeper connection between motion, charge, and wave properties, highlighting the complexity of quantum systems. If an electron moves in a straight line instead of a circle, its angular momentum becomes zero. This means that the charge associated with its motion also changes. The phenomenon isn't limited to electrons. All particles can exhibit this behavior, which is known as charge behavior of matter. This concept helps explain why both charged and neutral particles can have wave-like properties. Acceptance of the wave nature of matter was a turning point in physics. Louis de Broglie's proposal that all matter has wave properties, not just light, was confirmed by experiments with electrons. His mathematical formulas allowed scientists to calculate the wavelength of any particle, but also revealed that the original equations break down when the particle's mass or speed is zero. This realization led to the search for new, more general equation. Overcome the limitations of the original de Broglie equation, physicists realized that the relationship must be written in terms of charge behavior. By squaring both sides and rearranging, new equations were derived that apply even when the particle's mass is zero. This mathematical innovation expanded the applicability of wave-particle duality to a broader range of physical systems. Equations show that the charge of a particle at rest is not a fixed value but depends on its angular momentum and speed. When a particle is at rest, its angular momentum is zero, and the equations simplify. This leads to the concept of rest charge and rest mass, which are fundamental to understanding the wave properties of stationary particles. Even particles at rest can exhibit wave-like properties. When a particle is stationary, its kinetic and wave energies are zero, but it still possesses potential energy due to its position. This potential energy can be associated with a rest wave, which is a fundamental concept in quantum mechanics. The existence of rest waves shows that wave behavior is not limited to moving particles. In considering gravitational potential, the mass of a particle becomes linked to its wave properties. By substituting gravitational terms into the equations, we find that even neutral particles like neutrons can have wave-like behavior due to their mass. This insight unifies the concepts of charge, mass, and wave properties under a single framework. For any particle at rest, whether it has charge or not, there are two associated rest wavelengths, one linked to its rest charge and the other to its rest mass. The total rest wavelength is a combination of these two. This general formula helps explain why all particles, regardless of their properties, can exhibit wave-like behavior. It's now clear that all particles behave as waves because every particle can generate an electric field during its motion. Since this field is not constant, the particle can act as both a wave and a charge. Even particles without rest charge but with mass can generate a gravitational field, leading to wave-like behavior. This universal property is a cornerstone of quantum physics. Fields are fundamental to the existence of waves. An electric field arises from charge, while a gravitational field arises from mass. Both types of fields can give rise to wave-like properties in particles. This connection between fields and waves is a key insight that unifies different areas of physics and deepens our understanding of the universe. Whether a particle is moving or at rest, it can exhibit wave-like properties. Moving particles generate dynamic fields while resting particles have static fields. Both situations can be described using the same general principles, showing the universality of wave behavior in matter. Realization that all matter exhibits wave-like properties has profound implications for quantum physics. It explains phenomena such as electron diffraction, quantum tunneling, and the stability of atoms. These insights have led to the development of technologies like semiconductors, lasers, and quantum computers, transforming our world in countless ways. To summarize, all matter behaves like waves because of the fundamental properties of charge and mass. The wave nature of matter is not limited to moving particles. Even particles at rest can exhibit wave-like behavior. This duality is a central concept in quantum physics and underpins much of our modern understanding of the universe. For those interested in exploring these concepts further, a wealth of resources is available. Key references include Halliday and Resnick's Fundamentals of Physics, Survey's Physics for Scientists and Engineers, and other foundational texts in quantum mechanics. These works provide detailed explanations and mathematical treatments of the wave nature of matter and charge. Journey from ancient observations of static electricity to the modern understanding of wave-particle duality is a testament to human curiosity and ingenuity. As we continue to probe the mysteries of the universe, the interplay between charge, mass, and waves will remain at the heart of scientific discovery. This exploration not only deepens our knowledge, but also inspires future generations to ask new questions and seek new answers. Thank you for joining us on this exploration of the wave nature of charge and matter. We hope this journey has sparked your curiosity and provided a deeper appreciation for the wonders of quantum physics. Stay curious, keep exploring, and remember, every great discovery begins with a question.